The purpose of this lecture is to investigate what we mean by convergence of a sequence of random variables. Before we get into that, let's just review what we mean by convergence of a sequence of numbers. So let's say that I have a sequence of numbers. x1 is my first number, x2 the second, and so on. Then, in some cases, this sequence will converge to a number. Let's say, for example, that xn, the number at position n in this sequence, where n is any natural number, is given by 1 minus 1 over n, such that x1, the first number, is then 1 minus 1, 0, x2 is 1 minus a half, that's 1 half, and so on. I have printed the sequence in Excel, x1, x2, x3, x4, and so on. If we look at this sequence of numbers, we see that it will get closer and closer to the number 1. We can also see that if we make a graph of this sequence. So I have n on the x-axis and I have xn on the y-axis. x1 is 0, x2 is 1 half, x3 is 2/3, and so on. And we can see that this sequence seems to converge to the number 1 as n increases. In this case, we write that xn converges to 1 as n goes to infinity. So we would like to investigate a similar situation, but in this case, instead of having a sequence of numbers, I want to consider a sequence of random variables. I will denote this sequence by z. So z1 is my first random variable, z2 my second, my third, and so on. These random variables are all based on the same experiment. Nature picks an outcome in the sample space, and each of these random variables will then take a number. We also work under the assumption that all of these random variables are continuous. What we want to investigate now is the idea that this sequence of random variables converges to, well, not necessarily 1, but to a constant as n goes to infinity. Here is a simple illustration. I have a sequence of random variables, zn. So this one is my z1, that's my first random variable, my second, my third, and so on. Of course, what we see in Excel is the outcome of the random variable after the experiment has been performed. But we can simulate redoing the experiment by simulating new random numbers. So here we have another outcome from the sample space and new values of all of my random variables. What we see when we redo the experiment is that there is a lot of randomness in Z1. It varies quite a lot. As we move down the rows, going to the 10th random variable x10, we see that there is way less variation in x10, and it tends to always return a number very close to 1. This effect gets stronger and stronger as we move down the rows, and if we go all the way down to, let's say, 100, which is where I stopped, then the variation is very small. The first 3 decimals, for example, are always 1.000. So there is a clear tendency here for this sequence of random variables to converge to the constant 1. And this is exactly what we want to investigate in this lecture. How can we formalize the idea that the sequence of random variables converge to a constant? In this figure, this is the probability density function of my first random variable z1. It has an expected value of 1. The variance is quite large, so it tends to return in most cases a number between -1 and 3, which we see if we redo the experiment. This is the probability density of my second random variable, z2. It also has an expected value of 1, but it has a smaller variance than z1, so it tends to return, in most cases, a number between 0 and 2. I haven't drawn the PDF of z3, but this is the probability density function of the fourth one. This is even more centered around 1, pretty much always returning a number between 0.8 and 1.2. You can probably visualize how the PDF looks if we increase n. The higher the n, the thinner is this PDF and the higher it is. So let's try to formalize the idea that a sequence of random variable converges to a constant c as n goes to infinity. In my example, I have used c equal to 1, but in general, c is just an arbitrary real number. So let's create a small interval around this c. This is my c in my example, so I want to create a small open interval around my c. To do that, I pick a small number epsilon, which is greater than 0, and I create the interval c minus epsilon, that's this point here, to c plus epsilon, that's this point here. So in this picture, epsilon is this distance from c to the end of the interval. Once I perform the experiment, Zn will either end up inside the interval or it will end up outside the interval. Zn will end up in the interval if and only if the distance between Zn and c is less than epsilon. Before the experiment, Zn is random, so I don't know if Zn will end up in this interval or not, but if I know the distribution of Zn, then I can at least calculate the probability that it will end up in this tiny interval. So I can calculate the probability of Zn ending up in this tiny interval. Let's consider, for example, the probability that Z1 will end up in the interval. The green graph shows the PDF of Z1, and the probability of Z1 ending up in the interval would be this area here, which is very small. If we look at the probability that Z2 will end up in the interval, then we need to use the blue PDF. So that would be this area here. It is certainly larger than the probability that Z1 will end up in the interval. In this case, it looks like, I don't know, around a half or so. Not important what it is, but it's certainly bigger. If we look at the probability that the fourth one will end up in the interval, well, now in this case, it's all of this area. There isn't much left, a little bit in the tails, but we're fairly close to 1 now. So now we're getting close to 1. If you try to visualize this for even bigger values of n, then the PDF is even thinner and taller, so the probability that you will end up in the interval will become even bigger. This is the foundation for the convergence in probability concept. So we will say that this sequence of random variables Zn converges in probability to a constant c if for any epsilon greater than 0, that is for any size of this interval, no matter how small it is, the probability that Zn will end up in this interval always approaches the number 1 as n goes to infinity. No matter how tiny you make this interval, the entire mass of Zn will eventually be inside that interval as n goes to infinity. This is an idea used so much that we have special notation for the case, and we are going to write that the plim of Zn is equal to c. Plim is short for probability limit. So to check if a sequence of random variables converges in probability to a constant, we need to evaluate this probability and check if this converges to 1 as n goes to infinity. The bad news is that this probability is very often quite difficult to evaluate. The good news is that we have a very nice result to check for convergence in probability. And the result is as follows. If you can show that the expected value of Zn as a sequence of numbers converges to C, and you can also show that the variance of Zn, again as a sequence of numbers, converges to 0, then one can prove that the probability limit of Zn must be equal to C. If you think about this condition for a while, the first one says that the distribution will become centered at C as n goes to infinity, and the second condition tells us that the density will become infinite skinny and infinitely tall as n goes to infinity, and that's what we need for convergence in probability. I should mention that this is not the only way to define convergence of a sequence of random variables. There are other ones, such as convergence almost surely. Here is an important example. Let's say that I have a sequence of random variables x1 through xn, and it's a random sample. Denote the expected value of xi by mu and the variance of xi by sigma square. Based on this sample, I can define a new sequence of random variable. x1 bar, well, that's just x1. x2 bar, that's the average of my first two observations. x3 bar, and so on. So now n is arbitrary. We allow n to take any value. Then the probability limit of this sequence of random variables will become equal to the constant mu. This very important result is called the law of large numbers, LLN. More specifically, it's called the weak law of large numbers, and that is because we're using the concept convergence in probability. It's not hard to show this. We can just use the result above. The expected value of xn is the same as the expected value of each xi, so that's mu. We know that the variance of xn bar is the variance of the individual xi divided by n. So all we have to do is investigate what will happen when n goes to infinity. Well, the expected value of xn is mu for any n. It will continue to be so forever, so that converges to mu. The variance of xn bar will converge to 0. That's all we need to apply this result. And we can conclude that the probability limit of the sample average is mu.